Right, next chapter, 7.1, deals with diagonalization and quadratic forms, specifically with in this section with orthogonal matrices. Now, the definition of an orthogonal matrix is simply that it's a square matrix that has the following property. If you take its inverse is pretty much its transpose. And that's equivalent to basically saying that A multiplied by its transpose is the same as A's transpose multiplied by with A is the identity matrix. Okay, so remember the definition of an inverse. When is a matrix B an inverse of a matrix A? Is when A times B is the identity and B times A is the identity. Right, so both those properties need to hold for B to be A's inverse. Right, so the next example just asks us to determine whether the given following matrices are orthogonal or not. So let's look at the first matrix, which is this matrix. So all we can do there is just look at its transpose. Right, so there's A, and if we multiply it by its, well, if we look at its transpose is right, so if you take the matrix A and you multiply it with its transpose, you should check what you get there. And multiplying out, we see we get the identity matrix. Now remember, we had a theorem which said that if you have a matrix A and a matrix B and you multiply A with B and it's the identity, then it implies you don't have to check both BA and AB. It's going to immediately imply that B is A's inverse. Right, so you can easily see then that A's transpose is going to be its inverse, and so therefore that matrix is clearly orthogonal. Right, if you look at the matrix B and you multiply it by its transpose, we quickly see then that we see that the entry in the first row in the first column is 5. Okay, so I mean we don't have to go any further than that. B is clearly not orthogonal because multiplying it with its inverse or multiplying it with its transpose is definitely not the identity matrix. Okay, so that matrix is clearly not orthogonal. Right, this brings us to theorem 7.1.1. We say the following statements are equivalent for an n by n matrix. So this theorem tells us when a matrix is orthogonal. A matrix is orthogonal if a matrix is orthogonal, it will imply that the row vectors of A form an orthonormal set with the Euclidean inner product, and that will imply that the column vectors of A will form an orthonormal set in Rn with Euclidean inner product. And those three statements are mathematically equivalent. So 1 implies 2, 2 implies 3, and 3 implies 1. Right, so let's assume first that A is orthogonal, and we're going to prove property 2, which is that the row vectors of A form an orthonormal set in Rn with the Euclidean inner product. Right, this is going to imply that the matrix A multiplied by A's transpose is going to be the identity matrix. Right, now if you look at these, the R's denote the indicate the row number of the matrix A. Now remember that in the transpose, my rows become my columns and my columns become my rows. Right, so if you work the product between those two matrices out, you're going to basically see that the first entry in the entry in the first row in the first column is the first row of A's dot product with the first column of A's transpose, and that the first column of A's transpose is pretty much the first row of A. And pretty much the rest follows suit from there. Now, this is going to be the identity matrix, n by n identity matrix. What's that going to mean? It's going to mean that all these entries in the diagonal are going to be 1, right? And all the other entries are going to be 0. Alright, so that's going to mean that that r dot ri, which is the norm of ri squared, is going to be 1 for all I between 1 and n, and also ri dot rj is going to be 0 for all I not equals to j, n and 1. Okay, so this means basically that these row vectors are going to be, it's going to be first of all, they are going to be pairwise orthogonal, and they're all going to have norm 1, so therefore it's going to be an orthonormal set. Right, so that's going to imply that these row vectors are going to be it's an orthonormal set. Right, so let's just prove that 1 implies 3. So let's again assume A is orthogonal. Right, then we again have that A's transpose times A is the identity matrix. If we go and work this out, A's transpose, remember now the rows become my columns and the columns become my rows. So the rows of A's transpose are going to be the columns of A. So if we go and work that out, the C's indicate the columns of A. So the entry in the first row in the first column is going to be the first row of A's transpose, which is the first column of A, multiply or dot product with the first column of A. And the entry in the first row in the second column of A's transpose A is going to be the first row of A's transpose, which is the first column of A, dot product with the second column of A, and so the rest follows suit. Okay, so again that has to be the identity n by n matrix, right? So there we get the identity matrix, and again by the same argument, this is again going to imply that the set of column vectors are going to be an orthonormal set of vectors. So again, that's going to imply that the entries on the diagonal are going to be all the dot products. It's going to be 1. And all the other terms are going to be 0, meaning that whenever these indices are not the same, they are going to be orthogonal to one another. So it's an orthonormal set of vectors. Right, so the set of column vectors is an orthonormal set of vectors. Right, so you can also go and show that 3 implies 1. So assuming that the column vectors of A is an orthonormal set of vectors, then that's going to imply, obviously, that if you take A's transpose with A, which we said is this matrix here that we calculated. Remember now, the C's are they form an orthonormal set. So basically, that's going to be 1, 1, 1, and all the others are going to be 0. Okay, so basically that is clearly going to be that's going to be the identity matrix. Okay, and so it follows that A's transpose A is the identity matrix, which is going to imply that A's transpose is going to be it's going to be A's inverse. Okay, by that theorem from I think it's chapter 2. All right, and then you can also prove that by a similar argument, property 2 also implies property 1. And because property 2 implies property 1, that's going to imply 1 is going to imply 3, which we already proved. Okay, so therefore 2 is going to imply 3, and 3 is going to imply 1 as well. Okay, so we proved those 3 statements are mathematically equivalent. Right, so this example here, determine whether or not the given matrix is orthogonal. Right, so all we have to do here is apply theorem 1. So let's look at the row, or we can either look at the row vectors of A or the column vectors. So is the row vectors, or say, do the row vectors form an orthonormal set of vectors? So there's the first, let's take the first row, and let's look at the dot product of the first row, 2 row vectors. That's going to be 1 squared plus 1 over square root 6 squared. Okay, and that's going to be 1 plus 1 over 6, which is going to be 7 over 6, and that definitely right, that is not 1. So that implies that the norm, remember the norm is always a positive number, so the norm of R1 is going to be the square root of 7 over 6, which is not 1. Okay, so it's not an orthonormal. The row vectors, they don't form an orthonormal set, because there's at least one vector that's got a norm that's not 1. And remember, orthonormal means every vector in the set must have norm 1. Right, so that matrix is clearly not orthogonal. Alright, next theorem is theorem 7.1.2, which says pretty much that the inverse of an orthogonal matrix is orthogonal. You can see that from let A be orthogonal, right? So then obviously A's inverse is A's transpose. Okay, and from there we have that A's inverse's inverse is going to be A's inverse's transpose. Okay, so that is going to be, it's going to obviously imply that A's inverse is orthogonal. Okay. A's inverse is A inverse transpose. Right, the second property is a product of orthogonal matrices is orthogonal. Right, let A and B be orthogonal. Then we know that A's inverse is A's transpose and B's inverse is B's transpose. So that's going to imply that if you look at A times B, and you look at its transpose, that's B's transpose times A's transpose. That is B inverse A's inverse. We know that if A and B are invertible matrices, which they clearly are, then that becomes, by chapter 1, it becomes A times B's inverse, which implies that A times B is orthogonal. This one is pretty easy to show as well. If A is orthogonal, the determinant of A is either 1 or minus 1. If A be orthogonal, then we know that A's inverse is A's transpose, right? So that from there, we are going to have that A's inverse with A is the same as A's transpose with A times A, and that's going to be the identity matrix. And that's going to imply that the determinant on the left-hand side is equal to the determinant on the right-hand side, A's transpose times A. And that is going to imply that the determinant of the identity matrix is 1, and the determinant of that is the determinant of A's transpose multiplied by the determinant of A. Okay. Alright, so therefore we can replace the determinant of A's transpose with the determinant of A. So it becomes determinant of A squared is equal to 1. So therefore we can then from that deduce that the determinant of A is either 1 or the determinant of A is minus 1. Right, so here we are asked to show that that matrix is not orthogonal. Well, alright, so if we look at this matrix and we can use a contradiction here. Let's assume for argument's sake, right, that let's suppose A is orthogonal. Then by my result means the determinant can only be one of two things, either 1 or minus 1. Right, now if we look at the determinant of A, it's going to be minus 9 over 25 minus minus 16 over 25. Right, now because we assumed that A is orthogonal, it must have a determinant 1 or a determinant minus 1. Okay, so working the determinant out, we get 7 over 25, which is definitely not 1. So that's a contradiction, okay. So therefore that matrix A is not orthogonal. A is not orthogonal. Right, so that brings us to Theorem 3, 7.1.3. This one says that if A is an n by n matrix, then the following statements are equivalent. So A is orthogonal is going to imply that 2 holds. If 2 is going to imply 3, and 3 is going to again imply, so we got the closed cycle there. 3 is going to imply 1. So let's assume A is orthogonal. So what we're going to do is we're going to consider this dot product right between these two column vectors, and that we know is going to be that's going to be the norm of this vector squared. Right, now that's going to imply that can pretty much be written in matrix multiplication notation. So what you're going to do is you're going to take the matrix AX. It's a column vector. You're going to take the transpose and you're going to matrix multiply that with this column vector AX, right? And that's going to be equal to X transpose A's transpose multiplied by AX, and we know that A is orthogonal, so A's inverse is its transpose. Okay, so that's going to be pretty much X transpose dot with X multiplied with X, right? And that is going to be the norm of the vector X squared, right? So basically that's going to imply that that term is equal to that term there, and that's going to imply then that those two things are the same. Okay. This is true for all, or for any column vector X. Right, let's assume that the norm of AX is the norm of X for all column vectors X. Two vectors X, Y in Rn. Then we know that the norm of A X minus Y, which is a column vector, is going to be the norm of X minus Y, according to my previous result. Right, so that's going to imply that the following holds. That's going to imply that the square between the two is the same, and that's going to imply that that is pretty much it's the norm of, well, it's the dot product between these two vectors, ax minus ay, and that is going to be the dot product between x minus y and x minus y. Okay, then we're going to apply our dot product rules, and so we're going to get the following. Alright, okay, so the dot product works like that. Remember, you take that term with that, take that term with that, take that term with that, take that term with that. So therefore we got this expression here on the left hand side, and that is going to be equal to x dot x minus 2 x dot y plus y dot y, and therefore that's going to imply that, first of all, this thing here is going to be what? It is going to be it's going to be the norm of ax squared, okay, minus 2 ax dot ay plus the norm of ay squared, and that's going to be equal to the norm of x squared minus 2x dot y plus the norm of y squared. And that's going to imply that, remember, this is equal to that, and that is equal to that. Okay, so that's going to be that's going to imply that that thing is going to be equal to that thing. Okay, so that shows that 2 implies 3. Okay, so I want to prove now just quickly that 3 implies A. Right, so let's assume that ax dot ay is equal to x dot y for all column vector, all column vectors in Rn. And let's look at let C1 up until Cn denote the n column vectors of A, and just define x as that column vector and y as that column vector. And work it out, those two out. Ax is going to be a column vector, and it's going to be calculated by x1 c1 plus x2 c2 up until xn cn. That's the first vector there. You're going to dot that with pretty much y1 c1 plus up until yn cn. Okay, and that's going to be equal to x dot y. So that's going to be the dot product of x with y. So that's going to be x1 y1 plus x2 y2 plus up until xn yn. Right, now it's important to note that I can do this for any vector x and any vector y. So I can make the x's and the y's anything I want it to be. Alright, so this means let's pick x. Let's pick x, the vector. It's got zeros everywhere except for 1 in the ith row. and y is got zeros everywhere except for 1 in the ith row. And now what we do is we go and plug it into this expression here. So what do we get? So that will imply that we're going to make all the x's except for the ith x. We're going to make that 1. Right, so for the ith, so once we go down the road there and we get to the ith x, we're going to get ci, xi, ci, and we make the, what we did was in the vector x, we made the ith x 1, so we're going to get 1 ci, and we're going to get zeros everywhere else, okay? And here we're going to get ci there, and we're going to get zeros everywhere else, okay? So we're going to get ci's dot with ci. So we're going to get ci's dot with ci. And on the right hand side, when we go down that road there, we're going to get eventually to xi, yi, and we replace xi with 1 and yi with 1. So you're going to get, so you're pretty much going to get, you're going to get 1 there, and you're going to get zeros everywhere else. So that's going to be 1, which will imply that if you take the dot product of C, the ith column, with the ith column, we know that that is the norm of the ith column vector squared, which is 1, which is going to imply that the norm of the ith column vector is 1. Okay, so it means that you can do this argument for every column. So every the norm of every column is 1, and what else? Now we need to look at the cross terms. So let's look now. What we do is now we let x be the vector with zeros everywhere and 1 in the ith row, and let y be the vector with zeros everywhere with 1 in the jth row. And we assume that I is not equal to j. So plugging that back in, what are we going to get here? You're going to get zeros everywhere except for the ith c. So you're going to get ci there somewhere, and then you're going to get zeros everywhere else. Here you're going to get to the jth c, and on the right hand side you are going to get, you're going to get 0, right? Because if once you get to the ith x, you're going to get 1, but the ith y is going to be 0 because I is not equal to j, and somewhere there you're going to get to the jth. You're going to get to the jth y, which is 1, but the ith the jth x is 0. So you're gonna get zeros everywhere, right? Right. So then, basically, what we have is we've got that the ith column vector multiplied by the jth column, or dot product with a jth column vector, is going to be 0, and it's going to happen because you can do this for all I and j. So therefore, well, I not being equal to j, you get that the dot product of the column vector, the column vectors, is either 1 when the indices I and j are the same, and when they're not the same, it's 0. So that will then imply that these column vectors is going to be an orthonormal set of vectors, and by the previous theorem is orthonormal. And that's going to imply that A, by the previous theorem, is orthogonal. Okay. All right, the following example I'll leave for you guys as an exercise. Give an example of a linear transformation on R2. whose standard matrix is orthogonal by making use of the above theorem. Then we just have this little thing on the change of an orthonormal basis. If S is an orthonormal basis, what's an orthonormal basis? It's a basis that is every vector in the basis has norm 1 and the basis is orthogonal. So the vectors are pairwise orthogonal to one another. Right, for an n-dimensional inner product space V, and if the coordinate vector of u with respect to S is given as one vector, and the coordinate vector of V with respect to S is given as that vector, then the inner product of u and V, you can just write that as, you can easily compute that as just taking the, you can easily take that as just the dot product between essentially these two vectors. And the norm can also be easily calculated. The norm of the vector will be, it's the coordinate vector with respect to the basis S, and it will just be the square root of the sum of the squares of each component of the coordinate vector. And then again, the distance between u and v is just going to be the sum of these differences squared, the square root of that. Just to see why this is the case, if you look at S, which is an orthonormal basis, and you look at the coordinate vector of u with respect to the basis S and the coordinate vector of v with respect to the basis S, then we know that we can write u as a linear combination of the mentioned vectors. And now it's very easy to see why this is the case. And you can express the vector v as that. Okay. Now what do we know about S? S is a orthonormal basis. So if we go and work the inner product out, you can break the sum up into two pieces. You can look at the cases where the indices are the same and where the indices are not the same, right? So we know what is going to happen to that. That's going to fall away. That's 0 because the vectors are orthogonal within the pairwise orthogonal within S. And what else is going to happen? This is going to be what? That's going to be equal to this term here. Well, rather it's going to be the sum where I goes from 1 up until n, ci, ki, and this is going to be what? That's going to be the norm of vi squared. And the norm of vi squared, is going to be 1. Right, so basically you get that the inner product of u and v is pretty much determined by the coordinate vector with respect to the basis in each case. Right, so we need to, this example is just to illustrate it quickly. So let P1 have their inner product defined by the following. What you do is you take Px and you take Qx. Remember, P1 is the set of all polynomials of degree at most 1. And this is how the inner product works. It takes A0 and multiplies it with B0 and times it by 2. And then it adds that to A1 times B1 and it multiplies it by 3. Right. So we say, well, it's given that S is an orthonormal basis for this inner product space. So now we are just asked to calculate the inner product of P and Q. Now, we don't actually have to now go and pretty much use this. We can actually just apply this theorem here. This theorem, you can see that the calculation of the inner product, You don't actually have to use the inner product directly. You can just look at the coordinate vector with respect to the basis. So again, we know how to do this. So what you do is you take 1 plus x and you want to express it as a linear combination of the basis vectors. So going back there, we see it's 1 over square root 2 plus k2, and that's 1 over the square root of 3x. So that then implies that k1 is square root 2 and k2 is square root 3, and that will imply that the coordinate vector of x with respect to the orthogonal basis S, or rather orthonormal basis, is going to be this. It's going to be this vector. All right, the other one. Right, so for the second one, we need to find k1 and k2 such that we have that, and that's then going to imply that that k1 is minus square root of 2, and k1 is, or k2 is 2 square root of 3. Right, so that implies that the coordinate vector of qx with respect to s is going to be this it's going to be that vector there. Okay. So now it's easy to go and calculate the inner product. Right, so the inner product of P with Q is now, according to my previous theorem, it's going to be the square root of 2 multiplied by minus the square root of 2 plus 2 times square root of 3 times square root of 3, and that's equal to minus 2 plus 2 times 3, which is 4. Okay, and the norm of P, according to my previous theorem, is then pretty much it's the square root of 2 squared plus the square root of 3 squared. So that is the square root of 5. And then the distance between P and Q is, it's going to be the square root of 2 minus the square root of 2 plus the square root of 3 minus 2 times the square root of 3. Everything squared, and that's going to be 2 times the square root of 2 squared plus square root 3, or not square root 3, that's minus square root of 3, which is 3, and that's going to be the square root of right. The last one is theorem 7.1.5. If V is a finite dimensional inner product space, then if P is a transition matrix from one orthonormal basis V to another orthonormal basis V, then it's just important to note that P is an orthogonal matrix. Right, so let's take two orthonormal bases, right? Let's take two orthonormal bases. Right, now if we look at any vector in B, call it Ui, and we look at the inner product of Ui with itself, then by the previous theorem, we have that it is pretty much the dot product between the two column vectors. This is the column vector. That's the coordinate vector with respect of ui with respect to the basis b prime. And if we dot these two column vectors, then it should give us a normal. It should give us 1, because we said this is a orthonormal basis. So therefore, its norm is equal to 1. And also, we've got that if we take the vector u with uj, where I is not equal to j, that's going to be the coordinate vector of ui with respect to the basis b prime. We take the dot of the coordinate vector, not ui, uj, with respect to the basis. And that's 0 because we said that B is an orthonormal basis. So the vectors are pairwise orthogonal. So remember, the transition matrix is the matrix where we take the columns to be these coordinate vectors with respect to the basis. Okay, and right, so that's going to imply that that's a transition matrix. So if you look at the transition matrix, and you look at its transpose, and you multiply it with itself, then the transpose of P, the first row of the transpose of P is going to be this column vector, and it's going to be and again the second row is going to be this column vector, and so on and so forth, right? So basically, if you were to go and work that matrix out, I'm just going to use C's again. It's going to be the first column of the transpose of P, or it's going to be the first row, which is the first column, inner product with the first column vector of P, which is basically this vector here. And then you're going to, again, you're going to take the first row, which is the first row of P's transpose with which is the first column of P, and you're going to take the inner product of that with the first, with the second column of P, which is this vector, yeah, okay. And again, so doing that we get, right, so there we get our matrix, and again these C's are just pretty much these vectors, yeah. Okay, and we said that that is pretty much going to be 0 everywhere except for the diagonal. Okay, so this is going to imply that the transition matrix is its own, well, the transition matrix has the property that its inverse is going to be its transpose. Okay, so basically it is going to be an orthogonal matrix.